Hello everyone and welcome. I am the Mumbling Drunkard, and today we'll be covering some algorithms and data structures related to a problem that I stumbled upon on a Discord server. We'll be covering a couple of topics in this video. The most important ones will be segments or ranges and segment trees. Technically, the segment tree we implement is not an actual segment tree, but rather a specialized implementation. An actual segment tree is supposed to return all segments that overlap a certain element, but we're only interested in getting the actual elements, and this lets us simplify the implementation by a lot. I will assume you know fundamentals like arrays, functions, loops, and other stuff like that, so objects and classes, and it's not all that important, but it will help you read the code easier. If you have any questions outside of that, feel free to leave them in the comments or locate my email address in the video description. I will respond when I have the time, and with that out of the way, let's get into the problem. So, the chef and queries problem was discussed on a Discord server that I frequent. At first, I was only throwing out ideas for how it may be solved, but then I started trying to solve it myself and found it to be quite fun. The problem goes like this. So, chef and queries, you are given a sequence A1 to AN, and chef wants you to handle Q queries. There are two types of queries. The first type is 1 LRX. Then for each I, L less than or equal to I less than or equal to R, add x plus I minus L squared to AI. And then the second type of query is just a single number. Find the current value of AY. And yeah. So it's a very simple problem. It's just literally 4 lines of text. But the solution is going to be a bit more complex. So the input is going to consist of first our n and q. N is going to be the number of elements, and q is going to be the number of queries. The second line contains the initial values for a. So this is going to be n integers, a1 to an. And then after that, we're going to get our queries, which is q lines. So yeah. The output should be or for each query of the second type, print a single line containing one integer, ay. Very simple. Constraints we're not going to worry about for now, although it is important to note that these numbers can get very large, and that's really going to be the crux of our issues later on. So an example is given here. The example is we have an n of 5 and a q of 4. That means we have a list of 5 elements, and we're supposed to perform 4 queries. We read in the numbers for A, or the initial values at least. Then we have a query of the first type, which says we should perform the first query with L equal to 1, R equal to 3, and X equal to 5. And that's what they've done down here. So let's see. They have, so that's 5, and then plus 1, and then minus 1, and then squared. That's just going to be 5 squared. And the next one is going to be 6 squared, and then 7 squared. Then we just add that to the initial values, which are given. And the second query asks for 2, or the second query asks for the third element, which is 52 right now. And then, well, the third query is really easy, and the fifth query, or the fourth query, I mean, is the same thing. So this seems like a very simple problem, and it is. But we are going to encounter some issues, and we can try to just do it the naive way. So on my screen now, I have the naive implementation, and or it's not really an implementation, it's just pseudocode, which describes the algorithm which we should perform. So we input n and q, we create an array of n elements, and then for n times, we input into a. Very simple. Then for q times, which is the number of queries, we input first the type of the query, so either 1 or 2. And then if the type is 1, we input our L, R, and X, and then for I in the range L to R, and I'm going to call this range inclusive, so the range 1 to 3 contains the numbers 1, 2, and 3. Then we just perform the operation. We add x plus I minus L squared. Very simple. If the type is 2, we input the index we want, and then we print AY. Very simple. We can move over to the naive implementation in C++, and this is going to be pretty much just a translation of the code. I have added some things. I've taken myself the freedom to make the array 1 element larger, and this is simply because the problem is 1 indexed, while C++ is 0 indexed. Adding an extra element allows us to use 1 indexing, which means we don't have to translate between 0 indexing and 1 indexing in our code. It just simplifies things. So for size I equal to 1, I less than a dot size plus plus I, C in AI. Very simple. We just read. Actually, this is wrong now. I'm sorry. This code was 0 indexed, but then I changed it. So no, actually, I'm being. Am I being silly? No, I'm not. Yeah, I'm sorry. So we read in the number of elements. We actually start iterating at 1. So that's why I was confused. Anyway, we read in, and yeah, we read in all the elements we want, and then we move on to the queries part. So for the number of queries, we read in the command, and then if the command is 1, we declare some variables L, R, and X. We read those in, and then for all elements I equal to L, I less than R plus 1, and plus plus I, AI, add this X plus I minus L squared. Very simple. If the command is not 1, we enter the else block, which means the command is 2. That's implicit. We could do it explicitly as well, but there's really no point to that. So we read in our Y, and then we print our AY. And this code runs just fine. So if I navigate to my naive implementation, I can see that let's just run make, just to make sure that it's updated. And then we can run that. If we enter the numbers from, if we enter the numbers from the example, we get, so that was 6 and 5, yes. Then we can apply the first query and the second query, and we get 52, which is what we expect. Then we can enter 4, 5, 7, and then 2, 5, which is 69. Very nice. So this code actually works great, and if we're going to try to run it, it actually works fine too, I think. Let's try to submit. I'll have to log in here, so excuse me for a second. So here I am at the submission page, and we can hit submit and just press OK, I suppose. So after a while of processing, it seems we have actually completed the problem. And if this were a contest, we probably would be happy with this, as we got our points and we're done. But if you take a look at this, we have 1 second of time allowed, and we are just below that by a tenth of a second, which is really not much to go on. So let's just imagine, or let's just pretend that our code actually failed and we ran out of time. There's a better solution to this problem. So before we take a look at the proper solution, we should have a look at why this problem actually is kind of difficult. So, and to explain that, we'll have to look at the constraints for the problem. 1 is less than nq is less than 10 to the 5th, which really it's not that bad. It's just 100,000, and then ai could be between 0 and a million, which is also not all that much. But then we start realizing that L and R are between 1 and n. And this is really where the problem arises, because we can have 10 to the 5th queries, and we can have 10 to the 5th elements. So 100,000 queries and 100,000 elements, and every query can span 100,000 elements. So our implementation is at worst a squared implementation, which means it's polynomial. It's O of n squared. And this is kind of bad, because we will ultimately, in the worst case, have to process not 10 to the 5th elements, or 10 to the 5th operations, I should say. We'll have to process 10 to the 10th operations, which is, if I'm correct, 10 billion operations. And CPUs are very fast, but they're not that fast. So say a 5 gigahertz processor could possibly, with proper pipelining and proper optimization, be able to perform the worst case scenario in 2 seconds. But we only have 1 second, so we have to improve our algorithm. So the problem with our algorithm is simply that it's too slow, and it already seems like we're doing the best we can. We are performing the operation for all the elements required, and we return the queries as requested. We could turn the problem entirely on its head, and instead of actually modifying the elements, we kind of lazily evaluate them. So we store a list of these L, R, and X values, and when we get a query, we could run through this list and see if it should be applied to our element, and if it should, then we do apply it, and then we return. Easy as that. The problem with this is that we can have equally many queries, and if we feed in 100,000 values for L, R, and X, then we have 100,000 run-throughs of this list, or we have 100,000 segments that could potentially apply to our element, so that when we finally get 100,000 queries of the second type, we're essentially stuck in the same place. So what we'll do instead is use something that's better than linear time for both operations. So both the application of the algorithm and the queries. But how do we do that? Well, we can take advantage of the fact that the operation is not applied to scattered elements, but rather elements that are side by side. And when we want to, we can actually manage these ranges with a tree structure. And when we want to apply an operation to a range of numbers, we apply to the highest node, that is completely covered by the range of interest. The idea is that we don't actually store any elements, but instead we store the information required to reconstruct any element on demand. If that explanation is a bit vague to you, that's because it is, and this problem is a whole lot easier to explain visually, which is why I'll be moving over to my camera. So here I have a tree, and we start with some initial values like this, so 1, 3, 13, etc. And you can see that all non-leaf nodes, that is, all nodes that are not on this bottom row, are set to 0. And I've also included some numbers here on the side of each of these nodes. They're not important right now. I will get back into what they mean later. You can try to guess in the meantime. Now, let's say we want to add 4 to the first 2 elements. We could do it the hard way by incrementing both elements by 4, like this. So this would be 5 then, and this would be 7. Very simple. But as we have already noted, this tends to make our code slow, and we do not like slow. So what we do instead is apply the operation, so add 4, to the highest node in the tree that covers both elements, or all the elements of interest. And does this one cover it? No. Does this one cover it? Well, yes, but it doesn't completely cover it, or rather, it's covering more than the range of interest. So what we do is add 4 here. And you can see now that we're actually not storing the final value. If I wanted to request the second element, I couldn't just look at this, because this would be wrong. It's supposed to be 7. But what I can do instead is start at this node and then look at the parent and the parent and the parent. And then I just add those. So 3 plus 4 is equal to 7. Very simple. So that's very easy. So if I want to add 7 to element 5 and 6, I just add 7 here. If I want to add 3 to the last 4 elements, I just add 3 on this node. Very easy. But what if we want to add something to the first 3 elements? We can't just apply it here. And we can't just apply it here, because this covers more and this covers less. And we can't apply it here. So what do we do? Well, it may be obvious, but we apply it to the least amount of nodes that fully covers the range of interest. So the range of interest is element 1, 2, and 3. And how do we apply it to all nodes that minimally covers this range? Well, say I want to add 5 to the first 3 elements. I simply go in and I add 5 to this. That covers the first 2 elements. So I said 5, this was 4, so this should be 9 now. And we're missing one element. How do we apply an operation to a single element? We just apply it to the element. Very easy. So this would be 18 now. So just to explain this algorithm, given a range and an operation, step 1, check the current node. If the range fully contains that node, so our range 1, 2, 3, apply the operation and stop recursion at that branch. If the range does not fully contain the node, check if the range overlaps with any children, and if the range overlaps, set child as current node and go to step 1. And once again, this is much easier to explain visually. We of course start at the root node, so take our operation of 1, 3, and we want to add 5. So that was the example from the problem. 1, 3, 5. And these two numbers is simply the range of elements that this node covers. So 1, 3, does that cover the range 1, 8? No. Does it overlap the left child? Yes, it does. So we recurse into the left child. Does it completely cover this one? No. So we check the left child once again. Does it completely cover this one? Yes, it does. So we apply our +5, and then we stop the recursion here. We move back up because this parent is not yet fully explored. Now we have a look at the right child. Does 1, 3 fully cover this range right here? No, it doesn't, but it does overlap. So we recurse into this. Then we go down, we check, does the range 1, 3 overlap or cover 3? Technically overlap. Yes, so we move into it. Does the range 1, 3 completely cover the third element? Yes, it does, of course. So we add 5. Then we go back up, then we check the right child. Does the range 1, 3 overlap with the fourth element? No, it doesn't, because 4 is not in the range 1 to 3. So we go back up, and since we are coming back up from a right branch, I will just go ahead and mark this with a check mark. This helps us as humans keep track of which nodes are fully explored and which ones aren't. And the machine doesn't really need this. It keeps track of it in other ways. But we as humans are stupid, and we need this. Then we come back up, and we see that, hey, this is now fully explored. Great. And we come back up, and the right side is not yet fully explored. Does this range 1 to 3 cover or overlap the range 5 to 8? It doesn't. And so we end it there. We're done. So now I've described this algorithm, but you may wonder, what if I want to add something to the center 6 elements? So element 2, 3, 4, 5, 6, and 7. So I want to perform the operation 2, 6, 6. I want to add 6 to elements 2 to 7. Actually, I'm being silly. This should, of course, be 7. Now, how do I do this? Well, I just follow the algorithm. So I start at the top node. I check, does the range 2, 7 completely cover this range? It doesn't. I check the left child. Does it overlap? It does. So I recurse into it. Does it completely cover it? It doesn't. So I check the left child. Does it completely cover it? No. Does it completely cover 1? No. We go back up. We go down. We see, yes, it completely covers it. So we apply our operation, which is add 6. So we add 6 here. I'm sorry, that should now be 9. Then we go back up, and since we are coming from a right child, we will mark this as explored. We go back up, we see right child is not yet explored. We check, does our range 2, 7 fully cover or overlap this range? Yes, it does. Does it fully cover it? Yes, it does. So we add 6 here. We go back up. We can mark this as fully explored. Now we go back up here. Does the range overlap this range? Yes, it does. So we recurse into it. Does it fully cover it? It doesn't. So we check the left child. Does it fully cover it? Yes. Apply the operation. Then we go back up. We check the right child. Does it fully cover it? No, it does overlap. So we check the left child. Does it fully cover it? It does. So we add 6. And that's going to be 13. Then we go back up. Does it cover or overlap this element? No, it doesn't. We're exiting from a right child, so we mark this as complete. we mark this as complete, and we mark this as complete. And we're done. We have applied our operation. And as noted earlier, if we want to get the fourth element, all we have to do is start at the fourth leaf node and then recurse upwards. So 9 plus 6 would be 15. The third element would be 18 plus 6 is 24. Now, what if we want to add 7 to all the elements? Well, this may be obvious, but it's very easy. We simply add 7 to the root node. And that's all there is to it. So now, say I want the fifth element. I start at 8, I add 6, I add 0, and I add 7 for a total of 21. Now, before moving into the implementation of this algorithm, I will first talk a bit about how we'll be representing the trees. So if we have a tree, as you see here, and it's one indexed, so the root node is going to be 1, and then it has a left child, a right child. Those have children themselves, and those have children themselves. We can represent this in an efficient manner. We could, of course, just use pointers, with 1 pointing to 2 and 3, 2 pointing to 4 and 5, but this can be inefficient and wasteful. So what we'll do instead is we will allocate an array, which is large enough to hold all our nodes, and with some... Oh, that is a very not... Oh, God. It doesn't really matter, but I want it to look nice, so... But let's just say it has some slots here. I don't know how many that is. That should be 16, I guess. And our root node is, of course, here. And this is 2, 3, all the way up to index 15. Now, say we're at the node with index 1 in this array. How do we get to its children? Well, the formula is very simple. We have our L is equal to I times 2. And then R is equal to I times 2 plus 1. And I is, of course, the index. So for the root node, that's going to be 1. We multiply that by 2 to get the left child, which is 2, or the index of the left child. Then the right child is just going to be 1 times 2 plus 1, which is 3. We can check that this works for the second node as well. So 2 times 2 is 4, 2 times 2 plus 1 is 5. 3 times 2 is 6, 3 times 2 plus 1 is 7. 4 times 2 is 8, 4 times 2 plus 1 is 9. You get the idea. So this is how we will actually be representing the tree in the code. It's a very efficient way, and it's actually my favorite way, because it makes everything much, much simpler. So for this implementation, I actually won't be showing any pseudocode, but I'll try to explain it thoroughly enough so even people without C++ experience can understand the code. I'm no C++ wizard myself, so the code could probably be a lot better and more modern, but this is my code, so I do what I want. The first thing you will see, except for the includes, which really don't matter, is class range. Range is my implementation of the numbers you saw earlier, so say 1 to 8 is the range that contains 1, 2, 3, 4, 5, 6, 7, and 8. It is inclusive, which means that start and end could be 1 and 1, and it will contain the element 1. If start and end is 1 and 2, it would contain the elements 1 and 2. We have some constructors here. The default one just sets start and end to 1. This is just a way that makes it easy to initialize anything else with some range without actually applying this range. Just makes things simpler. The other constructor takes two arguments, the start and end, and creates essentially a range that has a given start and an end. Very obvious. Our method called len, or length, returns the length of the range. So the range 2, 3, 4 would contain 3 elements. It has a length of 3. And then we have our contains method. Our contains method simply returns whether or not a range can fully contain some other range. So the range 1, 2, 3, 4 fully contains the range 2, 3, 3, 4, 1, 2, etc. It also fully contains the range 1, 2, 3, 4. It just means that a range contains at least all of the elements in some other range. Now, overlaps returns something else. It could also be called partially contains. It simply means that the range contains some of the elements in another range. I have to note that ranges are strictly ascending, which means that end cannot be less than start. This is really just my implementation of it. You could make it bigger and more usable, but I've decided not to. The next thing you'll see in the center of my screen right now is our node. This is a very, very simple struct. It's containing a range and an integer. I've chosen to name this integer invariant. You'll see why I call it that later on, but for now, just remember that it's the value of the node. And last but certainly not least is our segment tree. Now, our segment tree contains an array, or in C++, a vector of nodes, and we call this nodes. This is simply our storage for our nodes. Now, the second and third thing you'll see is this init function and apply internal. We won't be looking at these right now. At first, we will actually look at our public functions, or public methods, I should say. So first of all, we have our constructor for the class. So that's segment tree. It takes in a size argument, and you can see here these first two lines actually computes the power of 2 that is at least as large as size, and I think should be, I'm not entirely sure. No, it should be strictly less than. Yes. I'm sorry. So this reads in the size, of course, and we start with power of 2 equal to 1, and then 4, we don't declare anything here. But while power of 2 is less than twice the size, we multiply the power of 2 by 2, which is why it's a power of 2. This is done so we can find how large our tree should be. I've decided to make the tree strictly a power of 2 in size, because it makes the implementation easier. We don't have to check for missing nodes or stuff like that. We can just run the code. Then we initialize our nodes array, or we create an array with power of 2 elements. Then we move on to this init function, which initializes the first root node with the range 1 to the number of elements. And the number of elements is, of course, going to be the power of 2 divided by 2. And this essentially just makes sure that our tree can at least contain the number of elements we're interested in. Let's look at some of the helper functions as well. So set does some special stuff. It simply sets the element, or the invariant part of an element with an apparent index. So As I'm sure you're aware, the first element won't actually appear as the first element or as the first node in the array. It will actually appear as the whatever this equation equates to. So this is simply what this does. It sets the invariant part of an element. Really easy. Now, let's look at these two helper functions right here. So I have get and get mut. So get returns a constant reference to a node in our array, and get mut returns a mutatable reference. Mutatable just means that we are allowed to change the value that it's pointing to. So as an example, this set function relies on get mut because we have to change the value contained in the node. We can move back a bit and have a look at init. This simply fetches a mutatable reference to the index given, and it applies the range which is supplied to the function. Very simple. Then we check if we are on the root node. That is to say, we check if we are on a leaf node, I'm sorry. So all leaf nodes will have a range that has a length 1 because they only cover one element. And if we're at a leaf node, it means we don't have any children to check, and so we stop the recursion. If we're not at a leaf node, then we move into this part of the code. So we calculate the index of the left child, and we calculate the range that this left child should have. Then we call init recursively on the left child with this new left range. The same thing is done for the right child and the right part of the range, and recursively called here as well. This will simply construct the tree so that it has an invariant value of 0, as well as the proper range that it covers. So the root node, in the example of 8 elements, so a tree of 15 nodes, as was shown earlier, would have the range 1, 8. Its left child would have the range 1, 4, and its right child would have the range 5, 8. And then you just recursively apply that. Finally, we move into the most interesting piece of the code, which is apply and query. I will handle apply first, which is simply a wrapper for apply internal. This applies an ln_r, which is going to be the range, and an x. So this will call apply internal at the root node, and then with the proper range, and then with some x. So let's move to apply internal. We move on to apply internal, which, as you saw, takes an index, it takes a range, and it takes an x. So we first get the node at the index, and we check if our range contains that node. And if it does, we get a mutatable reference, and then we mutate it by adding x. If the range does not contain the node, that means we're moving into this else block. We get the index of the left child, and then we fetch the left child, and then we check if our range overlaps with this left child. And if it does, we recursively apply the apply internal method to that left child. Note that in this case we actually use the same range and the same x because we have to. The same thing is done for the right child, and that's really our apply internal function. It's very simple. It's a recursive definition, and it's exactly as I showed you earlier on paper. Now for the query function, it's a bit different. It returns an integer, and it takes in an apparent index. So the index of an element, not the index of a node. And then we reconstruct the node recursively with this query internal call, which takes the apparent index and transforms this apparent index into the index of the actual leaf node. So as you saw earlier, I was actually not recursing down the tree, I recursed up the tree. So I started at the proper index of the node, and then I went to the parent and the parent's parent and the parent's parent's parent, etc., and just added them up. This is essentially what this does. Then we return the invariant part of the node. This is of course very obvious, but I will still explain this query internal. This is of course very obvious, but I will still explain this query internal. So now that we have received the index of the proper leaf node, then we get the node, and if the index is 1, that is, we have recursed up the tree fully and we have arrived at the root node, we return the current node. And this is a marked difference between query and query internal. Query just returns an integer, while query internal returns a node. It actually returns the reconstructed node. If we're not at the root node, it means we are at a leaf node or a middle node. So we fetch the parent recursively, of course, of this current node, and the parent, I'm not going to show you why this is, but the parent is going to be at the index divided by 2. This is fairly obvious, but you can try it out for yourself. Then we return the current with the current range unmodified, and then the current invariant plus the parent's invariant. And this is going to, as I said, recursively construct the node. So in our main function, it's reminiscent of our naive implementation. It really does the same thing, except we're actually not performing the problem as we should. Right now we're just adding x instead of doing the x plus I minus L squared, but we'll get into that. So for now, this just takes in an L, an R, and an X, and applies that X to the range LR. And we can query the tree as well for elements. So let's just try that. We can run make, and then I call this segment tree, yes. So say the elements, we have 5 elements, and they have we have 4 queries. We can read in the values from the example, and I'll just zoom in here again, and then we can pretty much just do the example. So 1, 1, 3, 5. So that's going to apply or add 5 to the first 3 elements. Then we do 2 and 3, and we see that we get 8. So 3 plus 5 is of course 8. We can do 1, 4, 5, 7, and then we can get 2, 5, which should give us 12, because 5 plus 7 equals 12. Now, if you really want to, this last part is probably the easy part to see right now, but I'd recommend you go and try it yourself. I'd actually recommend you try this entire thing yourself. So now that we have solved this simplified problem, where we just add x to a range of elements in less than linear time, we move on to perhaps the more mathematical part of this problem. And you remember how I simplified this right here, so x plus I minus L squared. I just simplified that to a single x. We will bring this back in and do some clever trickery to make this value more compatible with our code. To show you this, I will actually move back over to my camera. So let's start out with our x plus I minus L squared. That is going to be equal to x plus I minus L times x plus I minus L. That is very obvious. Now, let's just calculate this. That's going to be x squared plus xi minus xl. Then plus xi plus I squared and minus li. Then finally minus xl minus li and plus L squared. Let's regroup these terms and simplify. So x squared plus L squared, and we have minus xl and minus xl, so minus 2xl. This is the part of the equation that doesn't change based on the position of the element. Now let's look at the parts with I. I will actually group this into an I squared and our Li, Li, Xi, and Xi. So that is going to be 2i x minus L. And these two are rather easy. This is going to be added no matter what, and this is going to be multiplied, of course, by I, as you can see here, and then added. This part is applied every time we call our apply function, or apply method, or at least every time an element is affected by the apply method. And to keep track of this, we will call this passes. And we will call this the invariant. And we'll call this the positional. Because this is invariant, it doesn't vary, it's just static, it's added no matter what. This value right here, I squared, is multiplied by the number of times we have visited this element in our apply method. And this positional part is applied or is multiplied by the I and then added as well. Just to check our sanity, we will perform this example once again and see that we get the correct values. So we have initialized our invariants with these numbers right here. That's very easy. Now we do the first operation, which is so the invariant part should add x squared plus L squared minus 2xl. So this is L, this is x. So we just calculate that. That's going to be 25 plus 1 minus 2 times 5 times 1. So that's going to be 26 minus 10. We should add this to the first three elements, the invariant part of the first three elements. So that's going to be, let's see, this will be 17, 26, and 19. 26 and 19. Now, for the positional part, that's much easier. We actually have to remove the I, though, because it's not going to be stored like that. So 2 times x minus L, that's going to be 2 times 5 minus 1. That's 2 times 4, that's 8. We should add this to the positional part of each element. And then we finally increment the passes of all affected elements by 1. So that's just going to be 1, 1, and 1. Now, you'll see that we're not actually storing the results, but we can easily compute these results. So I'm just going to write up the indices right here because it makes things easier. So to calculate the actual values of these now, we take the invariant part, we add the positional part multiplied by the index, and we also add the passes multiplied by I squared. So that's the index squared. So that's going to be 17 plus 8 by 1 plus 1 times 1 squared, which is 26. This one is going to be 26 plus 16 plus 4, which will be 46. This one is going to be 19 plus 24 plus 9. That is going to be 52. And this one, of course, is just going to be 6 and 5. And that's exactly what we expect. And I will allow you to do the next 2 queries by yourself, just to verify, but this is actually true. So now we're pretty much done with the problem. All we have to do is add the passes and the positional part to each node, and we modify our apply function to perform the algorithm. So we get the L, which is going to be the start of the range. We add or increment passes by 1. We add the invariant part, which is x squared plus L squared minus 2xL. And then we modify the positional part. We add 2 times x minus L. Finally, we have query internal, which simply adds passes to parent passes and positional to parent positional and invariant to parent invariant as before. And then our final query, which reconstructs the node by calling query internal, and it returns nodes.passes by index squared, plus the positional multiplied by the index, and then we add the invariant. Very simple. And with all those changes and no real changes to the original algorithm, we hit submit, we click OK, we wait for a bit, and it should come back with some better results. And as we see, it's much, much better. So 0.19 seconds and 0.17 seconds. If you remember earlier, our code actually ran in 0.9 seconds. So this is much, much faster. It's about 1/5 of the time, which is a great improvement. And that's really all I had for today. If you enjoyed this, and if you'd like to see more videos about algorithms or electronics and other stuff, you can subscribe, and you can comment, you can like the video, etc. And yeah, thanks for watching.